So if I've sent you a data set, which I think if you've emailed me one, I've gotten one to everyone. If I haven't, correct me, someone I sent like in the last 30 minutes. So, but I think everyone should have something that should work for that first assignment. And a couple of you I mentioned, I'll try to kind of build a little bit more of an interesting data set as the semester progresses. If I send you something, I don't love this feature, but like it'll send it to you as an email on Canvas. Like every time you guys email me, doesn't matter if you email me from Canvas or not, I get a notification on Canvas and on my email. I don't think that a lot of my Excel files sometimes are too big and they won't go through the Canvas portal. So if I'm sending you something and it looks like it has an attachment, if it doesn't open, always go to outside of Canvas. Go to your actual like Outlook or whatever you're using for that Ball State email, and try downloading it from there. Okay. We've currently got a lot of stuff out there. So that individual assignment is the first thing due. Just do at the end of the week. At the end of the day, Friday. Shouldn't be too bad. Once I've gotten you that data set, a lot of it's just kind of going through answering a few questions. Like I said, I think I mentioned last class, creating a graph. You know, at the very end, it could be something, it doesn't have to be a histogram, it could be a time series graph, right? You could pull out part of the data and graph it as, you know, a scatter plot. Whatever you kind of want to do there, it should just be selecting data and inserting one of those types. I don't want you to have to go through the whole count ifs. And you don't have to go through all of that for this assignment. For that Excel assignment, it'll ask you to build a histogram. There, I do want to see you kind of calculating those frequencies using that count ifs formula. And then, of course, that connect assignment, you can start kind of working your way through parts of that, especially after today's class. And on Friday, for sure, you should be able to get through a pretty good majority of that. We might have a couple questions that we still cover the material on next Wednesday, because we don't have class Monday. But that's kind of what we currently have out there. So any questions for me before we jump into material today? Just housekeeping stuff. Okay with that? Also, if you want to tonight, Econ Club's meeting at 6. So free pizza always entices me to go do things. So and economics is awesome. I have to say that, right? So, but I actually genuinely do mean that. And if you want to talk to me about it, show up at my office and we can talk econ for as long as you want. So we left off talking about, we introduced the idea of the mean, right? So we've got this data. We've seen the frequency distribution, but like we can kind of visually see where the middle of the data is, but there's going to be some issues that arise when we're trying to get different measures of central tendency, right? Like where is the majority of the data, right? So we talked about, you know, we have this kind of mathematical formula, but really all it's saying is take whatever variable you're interested in finding the mean or the average, we could really say that of, add up all the values that you have. So take every single observation value for that variable, add them all up. And then how do you find a mean? You divide by the number of numbers you have, which will be represented by capital N, that number of observations in the population data. Sample data, same exact thing. Right? You add up all those values, but now you divide by what we'll call lowercase n, which is the total number of observations in your sample data set. Right? So the notation difference there is just identifying population versus sample data. So mu, the Greek letter, we said Greek letters, population mean, X bar, we're kind of using this English lettering X, and so we say that's going to represent the sample mean. Okay? So if we wanted to find the mean for birth rate in the US, I can answer this example in the last class. Take every birth that you have in the US, add up every single baby's weight, and then divide by the number of babies that were born, right? In fact, you can get this data. Not super easy, but it is publicly available. I think I've got the Indiana births from a while back, so we'll work with that data set quite a bit this semester because it's real data and it's kind of interesting. So I don't think I showed you this maybe, but I guess it would be like an example, right? If I had some game, boggle, or you know, basketball, whatever it is. I've got a number of points that this person scored in each game. How would I find the mean? Just add up the points scored from every game, right? 20 plus 35 plus 15, all the way down to the last game. I then divide by the number of games that I have, or the number of numbers that I have, which here would be 7. Oops. And we can find the central tendency of this data, right? This point scored variable is on average, right? The mean is about 24, right? Just under that. Okay. So I might ask you a question like this. I showed you how to do one. You would then want to do one. It's pretty easy, so I'm not asking how to do it. Right? Hopefully, I think most of you know how to calculate a mean, or at least have done something pretty similar. So if I have commute times here, how would I find the mean commute time? I just add it up for every single employee, divide by the number of employees, the number of observations I have, which is once again is 7. And I can kind of figure out this is what, 45. So one thing I want to point out here is sometimes when I give you these answers, I don't want you to get too lost in the formula. Like if you accidentally hit an extra 0, so that you added like 500 or something, you might get a ridiculously, crazy answer. And so maybe up here, I could have put like, I don't know, 110 as a possible answer. So why do you know you could rule out 110 right away?
Because it's
Higher than any of the values here. We're looking for a measure of central tendency. So the central point of the data should be somewhere in between the highest and the lowest value, right? How could it be outside of that? I mean, it wouldn't make any sense, right? And so don't get too lost sometimes in kind of what you're entering in the calculator. Think about what the statistic that you're calculating represents. For us, the mean is representing kind of the middle part of the data, has to be somewhere in between the highest and lowest value. So it should be somewhere between 20 and 90. So if there was any answer up there that wasn't in that range, we could rule that out right away. Okay. So the other two measures of central tendency we have are the median and the mode. So the mode's pretty easy. It's just the value that occurs most often or most frequent in the data set. So if I was doing something like, recording the number of households with 0 kids, or sorry, I had a data set and it had the number of kids in a household, and I had it for like, I don't know, a couple thousand different households. Well, I would go through whichever number of kids showed up the most frequent, which I believe, if I remember what the data looks like, would be 2, right? As the most frequent number of kids in a household in the US. That would be our mode. All right. I'll kind of show you some pretty easy examples here, some small data sets in a second. The median, I'll give you the definition and kind of show you the process. And I think once I show you the process, it'll make a little bit more sense. But the median is going to be the value such that 50% of our observations are above that value, and 50% of the observations in our data set are below that value. So that might sound kind of like the mean at first, but I'll show you why it's not necessarily the case. Okay. Now, for an odd number data set, what we'll do is we'll arrange all the observations from smallest to largest. Okay. We're then going to say, okay, cross off the lowest value, cross off the highest value, cross off the next lowest, next highest. And I do that until I'm left with one observation in the middle. That way I know that I have the same number of observations above it as I do below that value. And so with an odd number data set, that last value left in the middle will be my median. If I have an even number data set, what happens if I use that process? I get 2 numbers left, right? I cross those, I have no numbers. So I've got 2 numbers left in the middle. 50% would be above and below those, but I don't have one value. So all I do is just take the average of those 2 numbers, right? When I say take the average, right? Well, I have the 2 numbers, add them up and divide by 2. Okay? So what does this look like? So if I wanted to find the mode for this point score data, what would the mode be here? So the mode is what happens the most frequent. There's only one value that happens more than once, right? So 35 is the only value for this point scored variable that has been recorded more than once. So it's the most frequent. Now with a small data set, what could sometimes happen when you're trying to calculate the mode? Let's say instead of 35, this was 45. Well, now everything only happens once, and I may not have the most frequent, right? There might be kind of a tie. So with smaller data sets, the mode isn't as useful, right? It sometimes may not even exist. Or you can imagine if I had a truly continuous variable, what's potentially going to happen when I try to calculate the mode? If I could measure everything out to an infinite decimal, I may never see any number happen more than twice, or more than once. Sorry, I may never see anything happen twice. But for most larger data sets, especially if we're dealing with discrete data, we typically kind of can calculate these modes. What would the median be here? Well, it'd be easier if I arrange this from smallest to largest, but what I could do is just, I've got a small data set, I can do this by hand, right? So what's the highest value? 35. What's the lowest value? 15. So I cross those out. Well, chose the wrong 35, but 35 and 15, right? Then what's the next highest, next lowest? 35 and 16. Next highest, next lowest, 28, 18. I'm left with 20 odd number data set, left with one value that will be my median. Okay. Any questions on that process? Like I said, this shouldn't be too tough, so I'm probably going through a little bit quicker. Okay with that? So let's try to see if we can use these eye clickers here today. And I will set this up. I think I've got it set up now. So you have a physical version or download the app, it all should kind of work. So if you're trying to calculate the median commute time here, right? How would we do that? So we just went through the process with the points scored variable. How would we do the commute time? All right, so I'll give you a little bit of time to work on this, and then we'll kind of talk about it. Forget who had the app last time. Is it working this time? Yeah, okay. So I think I figured out what I was doing wrong. Excuse me. All right, give me about 15 seconds or so here. I'm trying to talk about it. We're looking for the median commute time. Also, I always keep the frequency on AA. If you're curious about that with the physical ones, I just always keep it on AA to make it easier. The professor tells you that it's too difficult to get other people's names in there. It's not that difficult. All right, you haven't got an answer and take your best guess here. I think there's 14 of us. Anybody having issues getting theirs in?
Yeah, they're just.
Oh, hold on. There we go. That'd make it a lot easier, right? Yeah, yell at me next time. I was like, I've seen some confused looks. I'm like, what's going on? Well, I didn't even have the answer. Now you can kind of get the answer that you calculated up there, hopefully, right? All right, everybody got an answer in? Everyone okay with this? Now that the answers are up there? All right. So what should it be? Everybody wants to. Yeah. Yeah, all right. So it ends up being 40, but we can kind of work through this process. I don't think I have it set up here, so we'll just double check here. So another way you could do this, you can kind of do like before and just cross off the highest, cross off the lowest, cross off the next highest, the next lowest. Sometimes it makes it easier to arrange them from small to largest. Then it's very easy to like cross off these bottom three, cross off these top three, and you're left with that value in the middle, which would be 40. Right? Notice there's 50% of the remaining observations above it, 3 observations above that value, 3 observations below that value. Okay. Any questions on that? Shouldn't be too bad. All right, so. Oh yeah, I forgot. I only have one side of the board. So I guess for those of you who sit on the left, it's going to be a problem the whole semester. But let's think about 2 variables. And I'll move out of the way in just a second. All right. We've got one variable X, one variable Z. Really small data set. This is also 100, not 160. So if I want to calculate the mean of this variable X, I'm just going to write this. That's my mean of variable X, just using that subscript to denote we're doing 2 different variables here. So what would I do? Add all these values up and then divide by, I've got 5 values, divide by 5. So to add these up and divide by 5, I get a mean of 6. Right? That's the measure of central tendency. What ends up also being true about this data set is what's the median? Cross off the highest, lowest, next highest, next lowest. I also have this median of 6. Well, that's because I have a symmetric data set here, right? Every observation is equally as far away from that middle point of the data. Now over here, I've got a non-symmetric data set, right? Because, okay, these observations are equally far away from that middle value, but 2 is a lot closer to 6 than 100 is, right? So now if I'm calculating the mean of this other variable, and I add these up, I get what? 10, 20, 120 divided by 5. Also, I'm not admittedly the best with mental math. If I try to do it quick, sometimes I make an easy mistake. So if I ever do something wrong, let me know if you're better at doing math in your head, or check me on the calculator. All right. But I believe it's 24. All right, if I do that division. So the mean of this second variable is significantly higher. But what's going to be true about, I should have said the median for x here and the median for variable z. Well, the median for the second variable, cross off the lowest, highest, next lowest, next highest. The median actually ends up being the exact same thing. Now, which one is a better measure of the central point of this data? You can have a debate, right? There's pros and cons of using both of these, right? Because when I use the mean, because I'm adding up the actual values, if I have these really extremely large values, it's going to pull that mean really, really high up. But it's only one observation. So when I calculate the median, each observation, right, the value doesn't matter. It just gets crossed off. So these extremely large, or on the opposite end, extremely low observations won't influence my median nearly as much as those really large observations will influence my mean. Okay. So with a small data set, and this is I guess I can jump ahead a little bit here and I'll show you why this is true in a second. With a small data set, those extremely large values are going to influence my mean a lot more than if I have a large data set. I'll show you why in just a second. So for small data sets, sometimes the median is a little bit more of a reliable measure of where that central point of that data is, right? So I kind of have a nice visual here. If we have symmetric data, right, a nice symmetrical frequency distribution, right, everything's, for every observation that's on the left, there's one equally as far away on the right there. And so for symmetric data, the mean, the median, and the mode, right, how could I identify the mode from a frequency distribution? Well, that would just be where my tallest bar is, right? My tallest frequency, the highest point of that frequency distribution. So they all end up being the same thing if it's symmetric data. If it's right skewed data, what ends up being true is these extremely large values on the right pull the mean up quite a bit, but they don't impact the median near as much. So notice for right skewed data, I said the easy way to remember that visually is a long right tail. It's because those extremely high values, even though there aren't very many of them, they're very, very large. So they're pulling that mean up, but not impacting the median near as much. So when we have the mean be to the right of the median, it's not something on the slides, it might be good to write down. But if you have the mean be to the right of the median or larger than, you have a right skewed data set. So I don't even have to see the frequency distribution. You can tell me the mean and the median of a variable, and I can tell you whether or not it's right or left skewed. In this case, variable z, we would say has a right skew. The mean is to the right or is much larger than the median. So what do you think probably is true about left skews? Well, extremely low values will pull the mean down a lot, but not impact the median near as much. So when I have these long left tails, these really, really small values, potentially even negative values, are going to pull my mean to the left of my median or be less than the median. And that's really where that naming of left and right skew actually comes from. It's not that we have a long left and right tail, it's that this relationship between the mean and the median of whatever variable we're looking at. Okay. Any questions on this? Is this kind of making sense? So where's mine? So one thing I also want to show you. We'll keep these data sets up here for now. So this was, and I'll just do it for a sample data set, so I'll use lowercase n. This was how we calculated the sample mean. All right. So what we were really doing, we said another way of thinking about this, and I don't know why this. I'm gonna grab the wrong one. Let's see. There we go. So another way of writing this, we said, was take each observation's x value, add them all up, and then divide by the number of observations we had in our data set. Okay. So I can rewrite that a little bit differently, which is I'll get out of the way here. Right? If I'm dividing everything by n, that's the same thing as dividing each of these by n. When I divide by something, it's the same as multiplying by 1 over that. So really what we're doing here is saying, okay, there's n observations, and each observation's value for x should carry the same amount of weight when I'm calculating the mean. How much should that weight be? Well, it's 1 out of n observations, right? So the mean, what you're really doing is taking every single observation and weighting it 1 out of however many observations you have. So you're equally weighting every single value. Doesn't matter if that value is extremely large or if it's closer to the middle part of that data, right? Everything's getting equally as weighted. So if I have a small data set, what is 1 over n when I'm calculating the mean of z here? 1/5, right? Times the first observation's x value, so 2. Then 1/5 times the second observation's x value. And I'm doing that for all 5. So each observation is 1/5, right, of the entire mean. Well, what happens if I have 100 observations? Well, now that weight turns into 1 over 100. And now I've got 100 observations I'm factoring in. So each observation, even if it was an extremely large value, will carry less weight and won't influence my mean near as much. So when we're dealing with like really large data sets, what do you think happens to that relationship between the median and the mean? As n goes up, these weights, each observation carries less weight. So that was the whole problem with using the mean in a small data set, is that each observation was had a very large weight. So with larger data sets, the mean and the median, they don't tend to be near as different, right? And that's because these extremely large or extremely low values just can't influence the mean as much. They're still 1 out of a much larger number of observations now, as opposed to like 1 out of 5, okay? Now, if there's several very large values, that's a different story, right? But each observation, just one observation, won't influence the mean near as much when I've got 100 versus 5 observations, okay? Okay with this up to this point? So making sense. And I'm showing you this because I don't know if we'll get there on Friday, but for sure next Wednesday, we'll start talking about weighted means, and we'll kind of compare those to a classic mean. I guess if we want to call it that. So we're then going to move, we've got our 3 measures of central tendency, and we're going to then use those to calculate the next type of statistic we want that will tell us something about the data, which is, well, what's the dispersion look like, right? These 2 data sets have the exact same median, right? So if I'm looking at a measure of central tendency, I might think, well, these 2 variables are pretty similar, right? They have the same middle point, the same median. But one of them has a much larger range, right? So all we're doing with the range is taking the maximum value of the data, or for the variable, and subtracting the minimum value, right? So the range of this variable would be what? X. Largest value minus the smallest value, it's got a range of 8. This one has a range of 100 minus 2, 98, right? So although they have the same measure of central tendency, the measure of dispersion is much larger for the second variable, which makes sense, right? The range of its values is much wider. To kind of give you another example of this, let's do 2 variables. And let's say I've got 100 observations, and they're just 1 through 100. All right, keep it easy. Then I've got another variable. And here I should have done dots here, right? I've got 100 observations. They're all 1, except for the last observation would be 100. Well, the range is great. It's going to tell me how, the difference between my smallest and largest value. So here, if I'm looking at this commute time data set, the highest value is 90, the highest value is 90, the lowest value is 20. I've got a range of 7, right? If I look at these 2 variables, what's the range of each one? They both have the lowest value of 1. They both have the highest value of 100. Here's where we run into the issue of the range isn't that useful. I mean, it's somewhat useful, right? I mean, we showed with the other two variables that had the same median that, oh, we can see there's a difference in the variable because the range is larger in the one. But here, you know, the range looks identical between these two variables. So I go, oh, okay, there's the same amount of variation, right? Thinking of dispersion. Dispersion is like how much most of the observations vary from that middle point. Another term that we often use, and I typically say instead of dispersion, is variation, right? How much variation is there in the data? Well, if I base it off the range, I would say these two variables have the same amount of variation. I mean, this one literally has 99 observations that are all the same value, and only one of them is different. I'd say there's a lot less variation in this data or in this variable than there is where I see 1, 2, 3, 4, 5, 6, 7, 8, all the way up to 100, right? Okay, so I know that I've got to go a step further, right? This measure of dispersion or variation is not that useful. Now, it'll be useful in some other things that we're going to calculate throughout the semester. That's why I introduced it here, and it's like the most basic, right? It's a very quick snapshot. You can calculate it very easily. We actually already know how to do it in Excel. Doesn't matter if I had 10,000 observations. We have that min and max function. We calculate that range very, very quickly. Okay? So the next thing that we're going to do is come up with a better measure of dispersion or a better measure of variation, which we'll call the variance. Okay. So the variance, we're going to use the notation. If it's a population data set, Greek lettering, we'll use sigma. So the variance would be sigma squared. Okay. I'll kind of talk about why we're doing this in a second, because we have another metric, which is the standard deviation. I think I've got, no, I don't have it on this slide, which would just be sigma, right? And so the variance is like the standard deviation squared. But we'll get into that in a little bit. So this is the formula for how we calculate that population variance. So let's think a little bit about what this is going to do. So before we even calculate it, we know that what it eventually should tell us is how much variation exists from the central point of our variable. So we start thinking about this. This summation sign means start with the first observation, do what is ever to the right of this summation sign, right? So start with the first observation, take its value for that variable x, subtract the mean of that variable, and then square that. Right? I'll then go to the second observation, take that observation's value for x, subtract the mean, and then square that value. I'll then do that for every observation, and then that summation sign means add them all up. Right? So once I add those all up, I then divide by the whole number of observations I have, and we say this would represent my population variance. So why are we doing this, right? So I'm going to skip ahead a little bit here and come back to this sample. So the first thing we have to do, right? This variance is the measure of like dispersion or variation from that middle point of the data. But we have to know what the middle point of the data is, right? So we're going to calculate the mean. Okay? Once we have that population mean, we said we're going to subtract that mean from every single observation's value for that variable x. So we'll call this each observation's deviation from the mean, right? So each one of these deviations, right, is going to tell us, well, this observation was this far away from that central point, or the amount of dispersion from this one observation was whatever that observation's value was minus the mean. Now, eventually we said we're going to add all those up. So we're going to take every single observation, figure out how far away it was from the mean, add up all that variation, right? Every observation is just one, point of evidence that there's, variation from that middle point of the data. We also said at the very end, we were going to divide by the number of observations we had. So before we fill the whole equation out, think about what this would do. It would take the deviation that we saw from any one observation from that middle point of the data. It would add up the deviation of every single observation, and dividing by n, it's kind of like what we're doing with the mean. What we're really doing would be saying every observation is going to have 1 over n weight. And so each observation's deviation from the mean will be weighted identically the same. So the variance is almost like an average or a mean variation from the mean, right? We're picking up the average or the mean variation from that middle part of the data. Okay. Now I left one thing out here from the equation I showed you before, which is that I should be squaring these deviations. Okay. So why am I going to square these deviations? Well, let's stop for a second. If I were to just look at observations difference from the mean, what's going to happen for every observation that's below the mean? That difference would be negative, right? It's going to be a smaller number than I'm subtracting. For every observation that has a value above the mean, that deviation would be positive, right? Well, when I then add them all up, they're going to like cancel each other out, right? So what we ultimately kind of are worried about is we don't care if the observation is to the left or the right of the mean. We just care that it's evidence that there is variation. So one thing we could do, I don't know I guess I have a rough idea based off of the survey of what your math background is, but I don't know each person's because I didn't look at every single person's individual response. But what's something I could do to maybe fix that? Other than squaring it, which we know we're already in. If I don't care about what side of the mean I'm on, and I want to know like the average deviation, but if I have observations below, some observations above, those would cancel each other out. What's something else I could do to that difference or that deviation? So have you heard of absolute values before? A couple people. So when we'll use absolute values throughout this course, which is why I'm introducing them now. We're not using them yet, but like this is the idea. So if I take the absolute value of something, I'm essentially ignoring the negative sign, right? You can think about it as I'm multiplying or I'm just dropping that negative sign, right? So it doesn't matter if I was 5 below the mean or 5 above the mean, I would treat that as a deviation of 5, right? That way I would kind of be able to calculate the average variation from that middle point of the data. Now, we're going to do something a little bit trickier than using absolute value, which is squaring that deviation. So why does squaring that deviation do the same thing as taking the absolute value? Well, if I have observations that are below the mean, that deviation from the mean will be negative. A negative times a negative is a positive. If I have an observation above the mean, it's a positive deviation, and a positive times a positive is a positive. So now my deviations squared will all be positive, right? So what has to be true when I'm calculating my variance? When I square every deviation, they're always going to be positive. So when I add them all up and divide by n, my variance will always be positive, right? I'm not dealing with any negative numbers. So we know our variance will always be positive, right? So really what we're doing is capturing the average deviation from this middle point in the data, but by squaring it, we address this fact that we don't care if the observation was below or above the mean, it was still evidence, right? Whether it was 3 above or 3 below, it was still evidence that it was far, it was varied from that middle point of the data. Okay. Now, what's another thing that squaring it does? Well, if we think about this, so let's say my mean is, I don't know, 5. And I have some, I don't know, value that's 6, and then we'll do 7 here just to kind of show the point. And actually, we'll do 3. Okay. So I've got 3 values. Sample, like there was more in the data set. I'm just showing you 3 of them, like a snapshot, right? So if the mean was 5, when I calculate the deviation from the mean squared for each one of these observations, well, what happens? This value is only 1 away from the mean, right? So when I take that difference, it would be 1. 1 squared is what? You guys don't know what 1 squared is? 1 times 1 is 1, right? How far away is this second observation? Well, it's only 2 away from the mean, but instead of adding a 2 to that numerator of the variance, I take that deviation, it was 2 away, and I square it, so I actually would add 4. Right? And then 8, well, it's only 1 more unit away, right? It's only 3 away from the mean. But instead of adding just 1 more unit to that numerator of the variance, being 3 away, that deviation of 3 squared is 9. So you can imagine as I move further and further, observations that are further and further from this mean or the middle point of the data, we basically like over penalize that variable, right? We say the further away you get, we're really going to add a lot more to the variance, right? And it kind of, these outliers end up contributing a lot more to this variance than values that are really close. Yeah.
So what's the purpose of the variance? What do you do?
So eventually we'll start doing things like creating to figure out probabilities that you see certain values. Given that you know the mean of the variable, you know there's a X% chance that I see that variable take on a value above this. Right now, that's way down the road. For now, we just want to think about it as we can identify or we can compare. So I'll give you a nice easy one. So let's say we have income, right? And maybe US and Canadian income looks pretty similar if we just look at the mean. I think it's, I don't know what the number is, but they're very close, right? But I then look at the variance for income in the US and compare that to the variance of income in Canada. And I see that the variance in the US is much, much higher. Right? Well, what that's going to tell me is that even though on average, the citizens in these countries are making about the same, but I've got a lot more inequality in the US than I do in Canada, right? Because if I looked at every single income, if I had the population data set, there'd be a lot more on average variation from that middle point. So, you know, economic inequality, income inequality would just be one thing that we could use it for, right? And it's harder to compare across variables. Like, so come back to this in just a second. I'll add some things and I'll come right back to it. So we'll talk about the sample here in just a second. Where do I have this? I've skipped over it already. Yeah. So the units of measurement of the variance will be whatever that original variable X was in. So if I'm doing income, my variance is in terms of dollars, right? So why is it then hard to compare the variance of, say, income in the US to height in the US? How can, I mean, just thinking about the range for income, I'm going to see a lot wider range of values as opposed to the range for height, right? So when it comes to comparing it across different variables, it's not as useful. But there's ways of adjusting this that we would then be able to actually, you know, you could cancel out the units and you have other statistics. But for now, thinking about its real usefulness is comparing things that have the same units, right? But it is also going to allow us to do things like build confidence intervals, determine these probabilities based off of normal distributions, and that'll kind of come down the road. Valid concern. But for now, we're just thinking about it's telling us something about, without showing a nice visual, it's telling us something about how much variation there is in the data. Okay. So we went through these steps. The only thing that differs, and I think I skipped over it here, glossed over, the sample variance, very similar. The procedure is identical. We'll go through every single observation, take the observation's value for that variable X, subtract now not the population mean, but you're dealing with sample data. So you'll subtract the sample mean, but calculate them both the same way. It's just one's the population data, one's a sample data set. We then take those deviations from the mean and square them. That's what we were doing before. We then add them all up, right? We had the deviation squared for every observation. We added them all up. But for a sample, what we'll end up doing is dividing by n-1, or the number of observations minus 1, instead of the total number of observations. So why do we do this? I punt on the explanation a little bit earlier on the semester at this point, and say, as we get to confidence intervals, this becomes a little bit more clear. But the main idea is that when I'm dealing with sample data, I know that the sample size has to be smaller than my population, right? It's a subset of it. So we know that we could end up with our sample variance being a little bit skewed, right? If we end up with some of those higher observations in our sample, as opposed to in the population, we know that they might be less likely. And so if I divide by n, right? Let's say our sample size was 10. If I divide it by 10, right? Instead of n-1 dividing by 9, what will be true about my sample variance? So if I only divide it by n instead of n-1, well, n-1 is going to be dividing by a smaller number. So if I divide something by a smaller value, the fraction as a whole ends up being larger. And if I divide by Give you an example. Let's say I added up all the deviations squared and they added up to 10. Let's say I had 2 observations. If I divide by 2, my variance would be 5. If I divide by n minus 1, I divide by 1, 10 over 1 is 10, right? So by dividing by n minus 1 with my sample data, I'm erring on the side of caution that it's always going to give me a variance that's a little bit inflated. And the reason why we do this is because once we get to confidence intervals and start calculating probabilities, we want to always err on the side of that the variation in the data is a little bit higher, right? Which then kind of gives us a little bit more, or our confidence intervals will be, interpretation of our confidence intervals will be more likely to be correct. That probably makes no sense right now if you haven't know anything with confidence intervals, but that's eventually where we're going. So for now, all you have to know is that we divide by n minus 1 when it's a sample to kind of overinflate that sample variance just to be precautious, okay? Because we don't want to assume that there's a lower variation in the data set. We're going to err on the side of caution that there's a little bit higher variation to the data set, okay? Any questions on that? No? Okay with that for now? So we went through these steps. We said the only difference was once we get down here, instead of dividing by n, capital N, the number of observations in our population data set, if it's a sample data set, we'll divide by lowercase n, the number of observations in our sample data minus 1. Okay. The standard deviation is the, I guess, technically third measure of dispersion or variation we're going to calculate. But notice it's the exact same thing as the variance, but I've done what? Take the square root, right? And that's why, you know, if I think about it, if I have my variance, if I take the square root of something that's squared, that cancels. So you can kind of think about it as the standard deviation is the square root of my variance, or said differently, the variance is my standard deviation squared, which my standard deviation sigma for the population and S for my sample, sigma squared and S squared, or calculated variance. So why am I doing this? Why am I just scaling my variance to make it a different statistic? So the reason why is because down the road, the standard deviation is has a lot more useful of an interpretation, right? Now, because we have to calculate the variance to then get the standard deviation, right? The standard deviation was just adding one more step, which is to take the square root. The variance is really your average measure of dispersion, right? And then we're just going to scale it by taking the square root to have a statistic that'll be a little bit more useful when we start to interpret things in terms of probabilities and percentages down the road. Okay, so for now, once again, I'm pumping a little bit. Hopefully, as the semester plays out, it's a little bit more obvious why we want to take the variance and scale it down to be the standard deviation. For now, all you have to know is you get the standard deviation from the variance, you add one step, which is take the square root. So if the variance is 100, the standard deviation is just the square root of that. The square root of 100 would be 10. And the units, I don't think I have another one here. The units are going to be the same thing, just whatever the original X variable was in. So its income will be in dollars, height will be inches or centimeters, however we measure it. And then, you know, that standard deviation will be important down the road. So we get some better interpretation when it comes to confidence intervals and hypothesis testing. Okay. Let me think if there's anything else I want to say here. I think what I have next is probably an example, but instead of walking through an example, what do I want to do here? I know what I want to do. All right. So we haven't seen how to do this by hand yet. Next class we'll start out with on Friday is I'll give you like this sample data set. We'll calculate the variance for it, kind of do it by hand. I might ask you to do it in hand, so you get a little bit of practice in class. I'll also then show you how we do it in Excel. But because I know part of the Excel assignment is doing measures of dispersion and measures of central tendency in Excel, I'll show you a little bit of Excel today. So we, I always try to kind of, I don't like having an entire class be Excel and an entire class not, I like to mix it in here and there. So we will just open up. Thought I had it opened up already, but I didn't. Let's open up that enrollments file. So for wherever we left off, or if you have the complete file you want to download from Canvas, And you really could use any observation here or any data set. If you have your individual data set pull up on your computer, you can actually use that. So as long as we have a variable, we can think about calculating things like the mean. You guys can't see this. All right, so the mean, the median, we could even do the mode if we wanted to. Right. So the mode, it's pretty easy. It's equal sign mode. And then we would go over. And actually, if I can keep this on the same thing, here I'm on that all universities. So I could select that very first observation, hold Control Shift or Command Shift on a Mac, hit the down arrow. Now when I hit enter, sends me back up to the top. And the enrollment that was the most frequent, although again, we're doing enrollments and there's a lot of different values. The mode's probably going to be that this only happened 2 or 3 times, right? So that might not be the most interesting thing to calculate from a data set like this, right? The median, if I use that process that I outlined earlier, right? Cross up the highest, cross up the next, that's going to be a pain, right? To do that by hand when I've got 2,400, I think it was, observations. So in Excel, I've got these huge data sets. How can I find the median quickly? Equal sign median. It's a built-in function. It basically goes through and like compares all the values to figure out what the highest and lowest, next highest and lowest are until it returns to you either for an odd number data set, it would give you that last middle value, or if it's an even number data set, it'll calculate the average of those last 2 middle values for you. All right, so it does it all for you behind the scenes. So we'll select that variable, Control Shift, Command Shift on a Mac, hold that and hit the down arrow, hit enter to close the parentheses and get back up to the top without having to scroll. And you can kind of see here, oh yeah, the mode was definitely probably not a real good identification of the central point of this data set because there were just so many different values we could see. So the median's about 3,500. We could then calculate the mean. So up to this point, you're probably thinking, oh yeah, it's probably just equal to mean, right? And I've been using the terminology of mean, but I alluded to the fact that it's sometimes also called the average. This is how we talk about it in our everyday speech. And so, or everyday language. So Excel not being, I guess, I don't know. I would expect that like computer programmer people would have kind of tried to name this a little bit more like theoretically correct or like really be on that, but they didn't. They just call it an average, right? Maybe they're making it more user friendly. So same thing, we select the entire variable after using that average function to find the mean. You can kind of see here, and the mean is quite a bit higher than the median. So if I'm looking at university enrollment, at least from this sample data set, what kind of skew, without even building the histogram, could I say that it has? Right skew, right? The mean is to the right of the median. So these extremely large values, which are kind of cheating because they're like community colleges like Ivy Tech, and they just their enrollments kind of all get grouped into one. We're greatly influencing our mean, but not impacting the median near as much. So we've got kind of these extremely large values for a right skew distribution. Any questions over on those 3? It's not too bad. I don't want to keep you guys over. So I'll jump back into Excel a little bit. It's not overly hard. There's some built-in functions for calculating the variance and the standard deviation. I can show those to you next class. Well, nothing crazy. Once again, it's like a built-in function. You select the data. But I want to work through how we do it by hand. So you can kind of, I think working through it by hand lets you think about what the statistic is actually measuring a little bit better. So we'll kind of walk through that, finish up measure of dispersion, and yeah, it should take us into the next week. Just in case I forget Friday, I'll mention now since I am remembering today. Remember, Monday is Labor Day, so we won't have class. We only meet Wednesday and Friday next week. Okay. All right. I will see you guys on Friday.